In this lesson, we're going to be looking at determinants and Kramers Rule. This is section 6.5. So let's define a few terms and some notation before we get started looking at determinants. So a determinant is what we call a real number. It's associated with every square matrix. We have to have a square matrix if we're going to discuss determinant. That real number can be positive, negative, or zero. All right, some notation that we need to be aware of. Some symbols that tell us that we're talking about, our conversation is going to be about a determinant. So the notation we can use is one of these different various symbols right here. So the determinant of matrix A, if we use the uppercase letter A to represent the matrix, the determinant of matrix A can be denoted in the following ways. If we're finding the determinant, we can abbreviate determinant and just put DET of A. And then here, this is just with parentheses around A. So they both mean the same. Another notation that we can use that represents that we're finding a determinant is these absolute value bars around A. They're not brackets. Brackets around an uppercase letter would just mean we're having a conversation about the matrix itself, but this tells us right here that we're going to be finding a determinant. Okay, and I'm going to use this notation right here. Or we could use this little delta, this little triangle of A. This means to find the determinant, or even this last notation, but we'll focus on the absolute value bars. So what is a determinant of any square matrix? Well, let's start with a 2 by 2 matrix. So the determinant of a 2 by 2 matrix having these elements, and these just represent the different numbers in this matrix. So the determinant of this matrix, we have brackets, is denoted by changing those brackets to absolute value bars. How we find that number that's positive, negative, or zero is by using this equation, this little formula. So notice that you have absolute value bars here. That means for us to find the determinant. So the determinant, that positive, negative, or zero number, okay, is going to be found by finding the difference, subtracting two diagonals from the top left down minus the bottom left up. And what we're going to do is we're going to multiply. So what we can see here is that when you go from top left to bottom right, and I'm going to put a little arrow here, okay, I'm going to multiply this number times this number. So that's represented by this expression, A sub 1 times B sub 2. Minus, we always minus, we don't add. We subtract the product that we get from the up arrow. So right here, you can see in this expression, it's A sub 2 times B1, which is what we get when we multiply these two numbers in this position. All right, we can also refer to this difference as the value of the second order determinant. Second order just means that we have a 2 by 2 matrix. Now let's get to some examples of finding determinants. So we have two examples here. We have A and B. We have square matrices in both of these, uppercase A and uppercase B. So this notation tells us, given this matrix with the absolute value bars around, what we want to do is we want to start from the upper left and go down. So we're going to take 10 and we're going to multiply it by 5 and then immediately put a minus. We don't add, we subtract. It's the difference of the up arrow product. These two numbers are 6 and 9, so it's minus 6 times 9. So 50 minus 54. So the value of this determinant from this matrix is a negative number, and it's negative 4. Okay, we wish we always have 2 by 2 matrices because they're easy. So given matrix B, using the brackets, let's find the determinant, because the absolute value bars, of matrix B. So down arrow product, immediately put a minus, and then put the up arrow product. So this product is negative 32. We have minus. This product is negative 15. So when you do this work on your calculator, I think we're going to get negative 17. So for both my examples here, we got a negative determinant. That just worked out to be a coincidence. Okay. But we could have a positive or a zero answer for a determinant. All right, 2 by 2 matrices are easy to find the determinants because it's just a down arrow product times a minus an up arrow product. It gets a little bit more tedious when we're trying to find the determinant of a 3x3 matrix. So we're going to kind of read through a little bit of this, kind of understand the notation, and then we'll have a couple examples to do of finding the determinant of a 3x3 matrix. So a third order determinant is determined by a method called expansion by minors. So what do we do with the 3x3 matrix? Well, first we choose a row or a column or a row to expand about. So it's going to become wise here in a minute when we look at a matrix to choose any row or column, and it doesn't matter which row or column that has a 0 in it. You'll see why here shortly. All right, so first we're going to choose a row or a column to expand about. The elements in this row or column provide what we call 3 factors. So once you choose your favorite row or column, the elements within that row or column are called factors. So what's a minor? The minor of an element is the 2x2 determinant that remains after deleting the row and column of that element. So a lot going on there. So let's kind of take a peek into what that is from these examples. So this example says expand the 3x3 matrix, this one right here, about the first column. So I would lightly circle the first column. They want me to expand about that column. And what it said up here is that the elements in this column provide 3 factors. So in this circled column, I have the elements A subscript 1, A subscript 2, and A subscript 3. Those are called my factors. So let's find the minors from A subscript 1. Well, how do we find a minor? We delete the row and column of that element. So let's find A subscript 1. Here it is. If I lightly cross off the row and the column that A subscript 1 is in, notice that you have 4 remaining elements. That becomes your minor. So your minor is the 2x2 determinant that remains after crossing off a row and column of that element, A sub 1. So this minor would be B subscript 2, C subscript 2, B subscript 3, and C subscript 3. By creating this minor, notice that it's a 2x2, so it's going to be easy to find its determinant here, because we've done that already up here with 2x2 matrices. All right, so what is this saying? What's the minor that comes from A sub 2? Well, here's A sub 2. Lightly cross off A sub 2, the row, and the column that A sub 2 is in. Look at the 4 remaining numbers. That creates your minor. And certainly finding this determinant would just be the down arrow product minus the up arrow product. It'd be pretty easy. All right, what's the minor from A subscript 3? Well, here's A subscript 3, so cross the row, cross off the column that A sub 3 is in, and then just write the remaining elements to become your minor. Unfortunately, finding the determinant of a 3x3 matrix isn't as easy as taking and multiplying all these numbers together and subtracting all of these numbers multiplied together. Oh, would it be so easy? All right, so first of all, we want to talk about, do we know what factors are? Yes. Okay, that's what we find within the row or column that we're going to choose. And do we know what minors are? Yes. Those are the remaining elements once we cross off rows and columns. This is a minor. And this is a minor. Okay, we're building. We just have to kind of lay all this out. All right, so what's the definition of the determinant of a 3x3 matrix? Before we get to this lined box here, there's one other thing that we have to be aware of when utilizing this definition. Be aware that in a 3x3 matrix, we have a sign pattern going on. And we always start in the upper left-hand corner with plus, and then we alternate signs. So to the right of the positive sign, we're going to put minus, and then we return to positive. Right here, if this is positive, if we go down, then we want to change to a minus. So down from here, it'd be a plus. Okay, so this is our sign pattern chart that we're going to also be using. So now let's go back to the definition of the determinant of a 3x3 matrix. I've kind of given you a lot of information, but let's see if we can kind of put it into play. All right, so I can see here that to find the determinant of this 3 by 3 matrix, I look at the factors. These are called factors because you're multiplying by a minor. Look at these factors, A1, A2, A3. All of those are found in this column right here. I could use a row, but I'm using this column. Then what happened was when I crossed off the column and the row for A sub 1, I'm left with this minor, which they have recorded here. Here's A sub 2. So if you come over here to this element and you cross off the row and column, you're left with the minor B1, C1, B3, C3. And then for the third and final element in this column, which is our factor, the remaining elements make up this minor right here. But what's important to notice and why this sign pattern matters is the first thing I would do is when I'm finding the determinant of a 3 by 3 matrix is I'm going to decide on the row or column I'm using, and then above those elements, those numbers, I'm going to put the corresponding signs according to this sign pattern chart. Meaning A sub 1 is in the positive position, A sub 2 is in the negative, and A sub 3 is again in the positive position. Which now let's transfer that over to what we have here. A1 is positive, that's why there's not a plus here, but it's understood. Go down to A subscript 2. This number, whatever it is, positive or negative, needs to have a subtraction sign right here. And then A sub 3, the number that's above it is positive, so this is a positive term right here. Now, depending upon what the numbers are for A1, A2, A3, it could be that A2 in here is already negative, so this would be a negative number here with this negative here as well. It's very possible that this number in this position is -5, well, which means that this would stay -5. So I want to use the numbers exactly as they are, but then put the additional positive negative sign in front of them. All right, that's a lot, but we need to get to an example. It says, evaluate the determinant of the following matrix. We have brackets, it's a matrix. Okay, we want to expand about the second row. They're telling me what to expand about. Okay, if I'm going to make this a determinant, okay, then I'm going to want to put all these numbers, okay, in between absolute value bars. So this is a matrix, and then I want to find its determinant. Okay, I think I'm going to start down here because I'm going to need some more space. All right, so he told me to expand around what, the second row? Okay, that's a good choice because when you look at the second row, I kind of lightly circle it. Notice that in that row, there's a 0, and that's going to help us in some of our work. I always try and choose a row or a column that has at least a 0 in it. Now, could I have chosen the column here? Yeah, I could have because it also has the 0. And it doesn't matter what you choose, as long as we do the work correctly, we should end up with the same answer. All right, so we chose the second row. So we circled it. Next thing to do is above each of these numbers, these elements, put the sign pattern values. So if you look back at the sign pattern chart, remember we start positive here, so down here this is negative. So I'm gonna put a little negative sign above that number, -5. Then I'm gonna put a positive, and I'm gonna alternate back to a negative above this 0. Again, I got these from the sign pattern chart on the other page. All right, so to get this value of this determinant, let's start with the first number in my circled row. Okay, so I'm going to start with -5, but remember above -5 is another negative. So I've got -5, which will be positive in a minute. This is a factor, so I'm multiplying it by the minor. Well, if I cross off this row that has -5 in it in this column, I'm left with the numbers 1, 7, 3, 1. All right, now back to your circled row. The next number is 6, and above 6 is plus. So I'm going to write down +6. But then I need to come up with its minor. Well, 6 is here. I'm going to cross off this row and this column, leaving these numbers on the outsides to make up my minor. So 2, 7, -4, 1. All right, let's go back to the circled row. The next number is 0. Above 0 is a minus. So I'm going to write down a minus and then a 0 to be multiplied by this determinant. So crossing off this row and this column, I'm left with the numbers 2, 1, negative 4, 3. Okay. Now seeing what we have here, I'm going to go ahead and take this negative negative and make it positive 5. And I'm going to put like another bracket here. Because in this bracket, I want to put the value of this second order determinant. So this is a 2 by 2. So remember, it's to find this determinant, it's the down arrow product, or 1 times 1, minus, always put minus, the product of 3 and 7. I'm going to move on, plus 6. I'm going to do a bracket. Let's find the value of this second order determinant. So 2 times 1, minus, not plus, always minus for determinants, negative 4 times 7. Then over here, minus 0. And does it really matter what goes in here? No matter what you get in here, you're multiplying by 0. So that's the benefit of choosing a row or a column with 0, because then you don't have to even worry about finding that determinant. I'm just going to leave that blank because it's not going to matter. All right, so let's work with the brackets. So you'll have your calculator. So 5 times, this is 1 minus 21 is negative 20. Plus 6 times, let's find this number, 2 minus, I think this is supposed to be a negative 4. Sorry about that. 2 minus negative 28. Well, if you do all that on your calculator, you should get 30. So this is negative 100 plus, and this is 180. Let's go right to your calculator. So the determinant for this 3 by 3 matrix is 80. I could do this same, I could find the same determinant by using the third column instead of the second row. My numbers will look different, but if I did everything right, I should also end up with 80. Let's look at example 2. All right, let's expand about the third column. Okay, so I'm going to circle this column, and above these numbers, I'm going to put the sign pattern. So I know in that sign pattern, this is positive, negative, this is positive. So if this is positive above this 0, this is negative, and this is positive. Our work here should be not too cumbersome because we got 2 zeros, and that's going to make it nice. I'm going to come down here. All right, let's start with this first factor, 0. Above it is plus, so I'm just going to write down 0, and I'm going to write down the minor. And it really doesn't matter, but I'm going to go ahead and get it present here. So this 0, cross off the row and the column, and you're left with this minor. Go back to your column, look at your next number 3. Above 3 is minus, so I'm going to put a minus, and then I'll put a 3, and let's find its minor. Row, column, we're left with 6, 4, 1, 2. Go back to the circled column, go back to the last factor, which is 0, above it is plus. Row and column get knocked out, 6, 4, negative 3, negative 5. All right, we can see here that this is going to be 0 times some determinant from this 2 by 2 matrix, but the down arrow minus the up arrow doesn't matter what that is because you're going to multiply by 0. I'm not even going to fill that in. So now I'm going to go over here, minus 3 times, let's find this determinant. It's 12 minus the up arrow of 4. And then likewise here, this is going to be 0 times some determinant that I don't care about because that product's still going to be 0. So all of that will go to 0, all of this will go to 0, and I'm left with taking this negative 3 and multiplying it by 8. So the value of that 3 by 3 matrix, the determinant's value is negative 24. All right, so now that we know about determinants, determinants are going to be used to help us to solve a system of linear equations called Kramers Rule. So far we've learned different ways to solve a linear system. We've learned the substitution method, the elimination method, And Lord help us, we learned about Gaussian elimination and changing a matrix to row echelon form. All right, well, here's another method for solving a linear system. All right, it's better received than the Gaussian elimination. Okay, it's just a little cumbersome, but you know, some do like this better than the row echelon form. All right, so what's Kramers Rule? All right, given a system of equations like this, the values of the variables x and y can be determined as follows. If I want to know what x is and I want to know what y is, I create a fraction. So in that fraction, here's my fraction bar. Above my fraction bar in the numerator, I have, in this case, I have a second order determinant. And then I also have another second order determinant down here. To get y, it's the same thing. I'm going to put a determinant over determinant, get these two numbers, and then I'll have what y is. Okay. It says that right here, this can also be written more simply as that the x coordinate, this, can be found by finding the determinant of the x matrix divided by the determinant of the coefficient matrix. And y can be found by finding a determinant of the y matrix divided by just the determinant of the coefficient matrix. If we were looking for z, just so forth and so on, okay, I could use determinant d subscript z divided by d. Same thing if I was finding a w, it'd be dw divided by d. So we've got to know what all of this notation is so that we can solve for x, y, and z in our linear system. So just uppercase D is the determinant of the coefficient matrix. We're going to create a matrix just using coefficients. All right, what's D sub x? It's obtained from the coefficient matrix by replacing the x coefficients in this matrix with the constant on the right sides of the equation. That's a lot. We're going to do an example, but it's good to see the language. All right, what's D subscript y? Well, it's another determinant we're going to get from the coefficient matrix by replacing all the y coefficients with the constant on the right sides of the equation. That's a lot. Let's see what that looks like in a 2x2. Okay. All right, if we end up with getting a determinant whose value is 0, then the system is either inconsistent or contains dependent equations, and we'd have to use another method besides Cramer's Rule to determine the solution set. Okay, that's not going to happen for us, and I don't think it's ever going to happen for you, but just know that if you get a 0 for the D determinant, that you might want to go back to systems using substitution or elimination or even Gaussian elimination. All right, it says use Cramer's Rule to solve the system, not substitution, not elimination, not Gaussian elimination. All right, so if we're going to use Cramer's Rule, we've got to come up with the values of 3 determinants. So remember from that little formula that the x variable is equal to d subscript x over d, and y is going to be equal to d subscript y over d. So we have 3 determinants we have to find. We have to find the d determinant, the d subscript x, and the d subscript y. So let's come over here. All right. So this value, d, that's going to go here in the denominators, is found by choosing the coefficients of the variables. So everything's lined up good. The x's are lined up, the y's, and the constants to the right of the equal sign. So in the D matrix, let's just put the coefficients of the variables. So there'd be 5, 4, 3, and -6. I'm going to go ahead and set up the other ones as well. So what's D sub x? And what's D sub y? It's good to look at them together. Okay, it told us on the other page that we're going to replace the x coefficients in the D matrix, that's this one, we're going to replace 5 and 3 with the constants 12 and 24. So if you see an x here, that's what you're replacing up here in the D determinant. So 5 and 3 become 12 and 24, but we leave the y coefficients. Likewise here, notice we have a y. That means back up here in the D matrix, the coefficient matrix, we're going to replace 4 and -6. We'll leave 5 and 3. Those x coefficients are good, but we replace these coefficients with these constants right here, 12 and 24. So the D matrix contains only the coefficients, and D subscript X and D subscript Y have a replacement in either the X or the Y column. Okay, so now our work is to find these values so that we can put the numbers back in up here in these little formulas and find the values for X and Y. All right, 2 by 2, thank God. Okay, down arrow, minus, up arrow. Go to your calculator, and you'll get negative 42. No expansion by minors, don't have to choose a column, don't have to know about the sign pattern chart, thank God. Okay, you can multiply and get negative 72 and put minus and then do this product and you'll get 96. That's going to be a negative 168. Down product, I think that's 120, it is, minus, always put minus, and then come over here and find this product, 36. Doing that on the calculator gives 84. All right, so we have all the values of the determinants. Now let's go to the formula to find X. I'm going to take negative 168 and divide it by D's value, negative 42. Should work out to be a fairly nice number, and this one does. This actually works out to be 4. Likewise over here, Y can be found by taking 84 and dividing it by negative 42. And that's a nice negative 2. And then of course we're finding an ordered pair, so let's make sure and put it in the proper format, in the ordered pair format, 4, negative 2. Okay, so we'll do number 2, another one, using Kramers Rule to solve this system. If I had a choice, I wouldn't be using Kramers Rule. I'd be using the elimination or the addition method, because when you add down, the Y's cancel, and you'll be able to solve for the X's real quickly, and then go back and get Y's. So, but we're told to use Kramers Rule. So I see, let me do this. I'm going to get this ready here. My X is going to be found from this equation, and my Y from this equation. So feel free to stop and try it on your own, and then come back and see how you did. Okay, I see an X, that means I have to replace 2 and 1 with these answers over here, these constants, so that becomes 3, 3, but I want to bring down the Y. dy, this is going to change, but the X's from the original matrix will stay the same, 2, 1, and then these become your 3, 3s. Let's find the value of these 3 determinants, and then we'll be able to find the X and Y variables. So negative 2 minus, and then that's positive 1, that's negative 3. Negative 3 minus, and then go back and multiply 3. And that's negative 6. That's 6, I need my equals, 6 minus 3, and that's 3. So to find X, D subscript X is negative 6 divided by negative 3. So X is 2. For Y, dy is 3 divided by negative 3. Oh, I just see what I did here. I put another Y here. My apologies. That's a D. So that's going to be 3 over negative 3. All right, ordered pair form, 2, negative 1 is your solution. All right. So those are easy enough if they're a system, linear system with 2 equations and 2 variables. Okay. Unfortunately, we need to do an example of using Cramer's rule for a linear system with 3 equations. And I think I'll do that actually in another video. See you in a minute.